Alright, so we looked at matrix multiplication in the last video. I want to talk about a real simple operation that we can do to a matrix, and that is called the transpose of the matrix. So the transpose of an m by n matrix, m rows, n columns, matrix A, is denoted A with a superscript T. So be careful, some students get the transpose confused with the trace, and they both begin TRA. Trace, remember, was the sum of the main diagonal entries of a square matrix. The transpose is actually another matrix. Trace is a real number. So it's denoted this way. The ijth entry of the transpose of a matrix is equal to the jith entry of the matrix. In other words, we simply swap the row and column locations in a sense. So let me explain. If B is this matrix, notice this is a 3 by 2 matrix, okay, 3 rows and 2 columns, then what is B transpose? Okay, so the entry that is in the first row, first column is the same as the first row, first column here, which is -4. But the first row, second column entry here would be the second row, first column entry of the matrix, which is 0. So this is the second row, first column entry. That becomes the first row, second column entry. First row, third column entry, well, that would have to be the third row, first column entry, which is 2 in the original matrix. Okay, so the original matrix, this is the third row, first column. Now it's the first column, first row, third column. Excuse me. What about the first row, fourth column? Well, if we were going to have the first row, fourth column entry, we would need a fourth row, first column entry, but there is no fourth row. So this is where we stop on the first row. What about the second row, first column? Second row, first column would be first row, second column, which is 1. Second row, second column would be second row, second column, which is 6. Second row, third column would be third row, second column, which is 2. Okay, so here is the matrix. In a sense, here's the easy way to think about this, instead of by entry, which is this column, the first column of matrix B, -4, 0, 2, essentially becomes the first row. Do you see that? Column is swapped with row, and the second row becomes the second column. Or if you want to think about it, the first row becomes the first column, second row becomes the second column, third row becomes the third column. So you see how that works? That's the transpose. And notice the size is 2 by 3. Okay, so notice the row and column numbers swap as well. So that's what a transpose is. So if A is m by n, the transpose is n by m. And notice, looking back at our matrix products, both of these products would be defined. You can multiply either way, because in each case the inner number would be the same. A times A transpose, the n's would be the inner numbers. A transpose times A, the opposite order, the m's would be the inner number. So let's talk about now, go back to matrix multiplication. And I want to look at, now that we've got the trace down as well, I want to look at a problem where I don't give you the entries in the matrix, I just give you their sizes. Here's 3 matrices, A, B, C, and D, and these are the resulting sizes of these, the corresponding sizes of these matrices. What I want to do is look at these matrix expressions to see if they're defined, first of all, and if so, give the size of the matrix. So let's look at A times B. Well, A is size 3 by 2. I'm just going to write that above it, size 3 by 2. B is size 2 by 4. So can I do that multiplication? Yeah, because why? The 2 inner numbers, the number of columns of the matrix on the left and the number of rows of the matrix on the right, they have to match. Since they're equal, this is defined. And what is the actual size of the matrix? Well, remember how we get that? There's 3 rows from here and what? 4 columns from here. Right? So that's the size of that matrix. It is defined. Okay. What if we look at B times A? Well, B again is 2 by 4, A is 3 by 2, And if I look at the inner numbers now, 4 and 2, what do we know? They are not equal. That means that this is not defined. So we talked about that when we were talking about matrix multiplication. Notice, unlike regular number multiplication, matrix multiplication is not commutative. In other words, A times B is not the same as B times A. And that's going to be something you're going to have to really think about and be careful about, because you're tempted often with real number variables to interchange. You say A times B, well, that's the same as B times A, because 2 times 3 is 3 times 2. But these are matrices, and it's not true. So if you have an expression that has AB, you cannot write it as BA. Or if you have BA, you cannot write it as AB. They are not the same thing in general. And it's clearly not, because here you get a 3 by 4 matrix. Here you don't even get a defined operation. What about DCA? Can we multiply 3 matrices together? What do I do when I'm multiplying 3? Where's parentheses? Do I have to multiply D times C and then times A? Or can I multiply C times A and then times D? Well, the answer is you can do it either way. And so matrix multiplication is not commutative, but we'll see it is associative. I can regroup as long as what? We don't commute. We can't change the order. DCA is not the same as CAD or ACD. Okay. Let's see first of all if DCA is defined. How do we do that? D is 4 by 4. Let's go write those up above each one real carefully. C is 4 by 3. And A is 3 by 2. So if I multiply DC first, can I multiply DC first? Well, DC, the inner number is 4. Yeah, I can. And what's the resulting size? 4 by 3, the outer numbers. 4 by 3. So DC is 4 by 3 matrix. So can I multiply DC times A, 4 by 3? Yeah, because these numbers now match, the 4 by 3 and the 3 by 2. And what's the end result? 4 by 2. So this is a 4 by 2 matrix. It is defined. You could also actually do the CA first. If I just do the CA first, just the CA, what do I get? Same size for the inner right numbers, right? Number of columns here matches number of rows here, so I can do the multiplication. And I'm left with a 4 by 2 matrix. What about a 4 by 4 times a 4 by 2? Well, that's defined, and it's 4 by 2 as well. And it's the same thing. So I don't need parentheses in any way. You can put parentheses around the D and C or around the C and A, and it means the same thing. Matrix multiplication, we say, is associative. What about C transpose times A? Remember, the superscript T stands for the transpose. Well, if C is 4 by 3, what's the transpose size? 3 by 4, right? 3 by 4. And A being 3 by 2, these inner numbers, the 4 and the 3, are not the same, and therefore, again, we are not defined. Okay. I could do C times A, like we were talking about over here. C times A was what? 4 by 2, but C transpose A is not defined. Now, in the last two, we're going to add addition, so be careful. Is this expression defined? Well, let's look at AB transpose. What is that? So A times B, we already said, right, the 4 up above, A times B was what? 3 by 4. So this is 3 by 4. But it's the transpose, so the transpose changes that 3 by 4 to a 4 by 3. So notice the parentheses tells us to take the multiplication first, in this case, and then take the transpose. C is what size? C is 4 by 3. What has to be true for adding matrices? Do we have to match the inner number when we're adding? No, for adding they have to be what? The same size. Are these the same size matrices? Yes. So I can add them, right? Corresponding entries are added together. And what's the resulting size? The same as the size of the two matrices we're adding together. So remember, addition, we just need to have the same size matrix. And the resulting matrix is the same size. Okay, last one has a little bit more going on here. Look at all this over here. So B, right, well, we know B is what size? 2 by 4. So in order for us to add these together, what has to be true? This has to be a 2 by 4 matrix. Well, is it? Okay, we got a lot going on here. Notice I have to do A transpose and then C transpose, multiply them together, and then transpose that. So what's A transpose? A is 3 by 2, so A transpose is 2 by 3. C transpose. C is 4 by 3, so C transpose is 3 by 4. Can I multiply these two matrices together? Yeah, because these numbers here are equal. And I get a 2 by 4 matrix, right? 2 by 4. That's what the product inside the parentheses is, 2 by 4. But then I take the transpose again of that product. So the 2 by 4 becomes what? 4 by 2 for this whole thing. Can I add a 2 by 4 to a 4 by 2? No, I can't add. I can multiply, right, because these two numbers are the same. But I'm adding, they have to be the exact same size. This says 2 rows, 4 columns. This says 4 rows, 2 columns. So again, this is not defined. You do have to be careful. We're talking about addition or multiplication. Okay. So notice in all these examples, they're real nice. They're not actually asked to compute anything. Just say, is the product or is the expression defined? And if so, how do we go about, and if so, what's the size of the resulting matrix? Okay. What I want to look at then in is a little bit more about the properties of the transpose. And we're going to close out this particular video with that and with a little proof. So let's look at the properties of the transpose. We introduced the transpose just a minute ago. Number one, if I take the transpose of matrix A and then take the transpose again, then I get matrix A. That should make sense, right? Transpose, swap rows and columns. Transpose again, swap rows and columns again. You're right back where you started from. So that makes sense. The second one says add two matrices together, so obviously they have to be the same size, and then take the transpose. And that's the same thing as if you just take the individual transposes of those matrices and add them together. That should make sense, right? So if I add A and B together and get the resultant matrix, and then I take the transpose, that'll be the same thing as if I took the transpose first and then added, right? Because the transpose just swaps rows and columns. Adding just adds the corresponding entries together. If K is any scalar, then the scalar multiple, Ka, and then if you take the transpose of that, well, that would be the same as just K times A transpose. And that should make sense. In other words, again, you can do the scalar multiplication first and then the transpose, or you can do the transpose and then the scalar multiplication. That should make sense, right? If you have a matrix and you transpose it and then multiply everything by K, that's the same thing as multiplying everything by K and then taking the transpose. Okay. So 1, 2, and 3 I think are fairly obvious, pretty easy to prove. Number 4 is a little bit different, and we're going to prove number 4. 4 says if I have A times B, so that product, right, that's a multiplication problem. It has to be defined. If that's the case, and you transpose that, then that's equal to B transpose times A transpose. Again, provided the product AB is defined. So that is the situation when we are multiplying. Now you say, why did I write it B transpose A transpose? Why isn't it just A transpose B transpose? Well, remember, matrix multiplication is not commutative, so B transpose A transpose is not necessarily the same thing as A transpose B transpose. And in fact, it has to be in this order. It has to be in this order. So if you have a product AB and you transpose it, you get the transposes of those individual matrices multiplied in the reverse order. All right, so I'm going to prove this for you, and this will be your first taste of a proof. And you're going to write some proofs in this class. And so I'm just going to prove number 4. And I'm going to do a couple proofs involving properties of matrices. This is my first one. You're going to do one as well, and so you're going to follow the proof that I write here, and the next one as well. Actually, the next one will be even more like what you guys will be doing. So how do we do that? If you remember way back a couple videos ago, we talked about the fact that two matrices are equal if what? They are the same size and corresponding entries are the same. So when we prove something, that's what we're going to use. To prove this statement, I cannot simply create some actual matrix A and some actual matrix B, and do this operation and say, hey, it's the same thing. I mean, you can find a matrix A and B, plug in the numbers, and you'll see both sides are equal. That doesn't prove this. That just shows it's true for one particular combination. So we have to do it in general, and this is the way we're going to do it. So I'm going to sort of talk you through the proof here. So first, to prove, what we're proving here, that AB all transpose equals B transpose A transpose, we must show they are the same size. All right, we have to start there. If they're not the same size, they can't be equal. So let's start there. So let's start with something. Let matrix A be size, and I'm going to do M by N. Now what? You don't want to do like 3 by 2 or 4 by 4 or any specific numbers, because we have to do this in general. So I'm doing an arbitrary matrix, different number of rows and columns, so any matrix, and they could be the same, M and N could be equal, but I'm just saying in general, M rows and columns, right? And I need to clearly define matrix B size, so let's, and matrix B size what? Well, now we do have a little restriction, because A times B is supposed to be defined. If that's the case, and if AB is defined, then the number of columns here of A has to be the number of rows for B. So these inner numbers, remember, have to match. What about M? Does this have to be an M here? No, it doesn't have to be an M. It can be anything. So I'm going to call it R. Okay. So this has to be, this letter, the number of columns here, number of rows here, has to be the same in order for AB to be defined. Okay. So you start there, and so then we could say then AB is defined and is size what? These inner numbers N match, right? A is M by N, B is M by R, so resulting size is what? M by R. And I'll just go one step further. AB, then, that product transpose, which is this side of the equal sign, is what size? Well, if AB is M by R, when we transpose it, what happens? They swap. It's R by M. Okay. So that's this side. This side of the equation is a size R by M matrix. Now we have to show this side is. Okay. So we'll say similarly, on the other side, or on the other hand, or something, right? Looking at this side, B transpose is what size? Well, B was size N by R, so B transpose is R by N. And A transpose is what size? A was M by N, so A transpose is N by N. So that B transpose A transpose, can I do that multiplication? Well, let's see. B transpose R by N, A transpose N by N. Are the inner numbers the same this time? N and N, yes, they're the same. And what's the resulting size? R by M. Okay. And what do we have? B transpose A transpose is R by M. That side is going to be R by M size. And AB transpose, the other side, is R by M. So both sides are the same size. Okay, that's the first part of the proof. So you have to just do, and you'll notice in the proof, it's all these things we call letters, right? Words, sentences, yes. You're explaining in words what's going on. Do you have to write this? Yes. We are proving this, and it must be written in the English language, please. Going from left to right. Putting in periods. Now we do abbreviate some, and we have, letters for the sizes of the matrices and such. But that's what you're going to do. If you are uncomfortable with that, you shouldn't be. You're you are at the stage now where you should be comfortable writing things out, explaining essentially. So this is how we prove something, right? Showing two matrices are equal. We first show they're the same size. Now, here's really the mathy side. Now we have to show what? We have to show corresponding entries are the same. Okay, and so now what I have to do, well, I can't just, I don't know what's, it's size R by M each of these, but what I'm going to do is look at AB transpose, and I'm going to look at its arbitrary ijth entry. What's its ijth entry going to be? Okay, and what I want to show is that its ijth entry, so this is arbitrary, ith row, jth column. I'm going to show that's the same as the ith row, jth column of the matrix on the right. Okay. So first of all, what I want to say is, well, AB transpose, the ijth entry, would be the same as just AB, what? JI. What have I done here? So, going from the transpose of AB to just AB does what? We swap the rows and columns, right? So ij becomes ji. Remember, that's the definition of the transpose. So the ijth entry of the transpose of the matrix is the jith entry of the original matrix, AB. Okay, that's the first step. Then I want you to note that the product AB, this is going to be, we're going to call this the dot product. Remember, we're talking about the dot product? This is the entry in the matrix AB. This is the dot product of what? The jth row of A and the ith column of B. Remember, that's the definition of matrix multiplication. All right? The jith entry is the dot product of the jth row of A and ith column of B. Keep in mind, right, the first number is the row number and the second number is the column number. Usually I is the row, J is the column, but because we swapped, right, what was the row here, I, is now the column here, so keep that in mind. But to get the entry in the jith entry, this is the entry in the jth row, ith column of AB. You take the jth row of A, right, and you dot it with the ith column of B. That's the definition of matrix multiplication. So if you forgot that, you might want to go back and look at the previous video. Okay, but then the dot product of the jth row of A and the ith column of B is the same as the dot product of, well, the ith column of B, first of all, that's the same as the ith row of B transpose, right? The ith column of B is the same as the ith row of B transpose, right? Just looking at B, right? If I looked at that, right? So this is the dot product of that and what? The jth row of A. But the jth row of A is the same as the jth column of A transpose. And when I take the dot product, I kind of change the order of these two things. It doesn't matter the order they come in. Right, so dot product is simply multiplying two real numbers together and then adding them all up. So the order I multiply does not matter. But at any rate, these are equivalent expressions. But what is the dot product of the ith row of B transpose and the jth column of A transpose? That, by definition, is indeed the ijth entry of B transpose times A transpose. If I take the ith row of B transpose, dot it with the jth column of A transpose, that's the ijth entry of B transpose, A transpose. And that's the end of the proof, because that shows me that the ijth entry of AB transpose equals what? Equals the ijth entry of B transpose A transpose. When I end a proof, I typically put a little block like that and fill it in. So people write QED, which is a Latin expression, meaning that we have demonstrated what we sought to prove, but this is the proof. This is going to take you looking through it a little bit. The book similarly proves this. You can take a look and see how they wrote it. It's very similar to this. But this will be an adjustment. This will be something you'll need to work on, but use this as a model and direction. I'm going to do one more in the next section later on, and so you'll be able to see another illustration. Okay, so we're going to stop here. I got one more video I'm going to do next that will show us real briefly about another way we can use matrices to represent systems of linear equations other than just using the augmented matrix.